All right, well, welcome to this lecture on isotonic and buffer solutions. And I will warn you, this is part 1 of 3. We have a total of 3 lectures to get through this rather expansive chapter 11 on isotonic. A couple of different categories, isotonic and buffer solutions. We'll talk about pH as well a little bit later. But let's focus on isotonicity and osmotic pressures. And I will say this is an important lecture. Now, it's not as exciting as part 2. I like part 2 because we actually get to do the calculations and formulate the prescriptions for various eye drops and ophthalmic solutions. But you can't do those calculations if you don't have a strong understanding of, first of all, basic principles about osmotic pressure, because that defines what is an isotonic solution. And you can calculate the amounts of particles you need for isotonic solutions if you don't know how to do freezing point depression and sodium chloride equivalents and the like. So this is an extremely important fundamental lectures to make sure that you're up to speed and can understand then how to actually perform the calculations we'll do in part 2 when we formulate our ophthalmic solutions. So with that as a background, let's get started. The first topic to kind of review, and this should be a review for most of you, is osmosis. And it's what I was a little bit surprised was how important this understanding was. In fact, the very first Nobel Prize ever in chemistry was awarded in 1901 to Jacobus H. van Off in recognition of the extraordinary services he rendered by the discovery of the laws of chemical dynamics and osmotic pressure in solutions. This was a big deal. Now, unfortunately for Van Off, they hadn't invented the comb yet, apparently, but he did do a lot of work for this idea of osmotic pressure. And what that comes down to is that the flow of solvents, such as water, through a semi-permeable membrane from a dilute solution into a more concentrated solution to equalize the concentration of solute. So that's essentially the principle of osmosis, that with a semi-permeable membrane, like most biologic membranes on cells, are semi-permeable, meaning some fluid and some very small particles can get through, but larger particles, proteins, red blood cells, for example, cannot easily pass through these semi-permeable membranes. But fluid can and will move in the direction to minimize or to equalize concentrations of solutes, which are dissolved particles in solution. Okay, so remember, the take-home message is osmosis depends on the number of particles in solution, okay? And that depends on the dissociation then of electrolytes, especially in biology, since we have a lot of sodium chloride, potassium chloride, magnesium sulfate, things like that. They will break down into their components, ions, and therefore the number of particles that these molecules produce has the main driving force on the force of osmosis. So let's keep that in mind and do some practice here. So the reason this is important is a lot of time in pharmacy we dose things by mass or by weight, and the units of weight are in grams. We need to get past that because when we start doing these calculations as it relates to osmosis and isotonicity, we are basing it not on the weight of substance, but on the number of molecules. So, and further into the number of particles from those molecules. But let's start with just molecules. So remember, it's extremely important to be able to convert grams to moles for the calculations that depend on the number of particles. So let's do this for a couple of examples. The first 2 examples are pretty straightforward. We will convert grams to moles, the number of molecules for non-electrolytes, and then electrolytes, where we assume complete dissociation of those electrolytes. Unfortunately, that's not always the case. So we'll also have to, and this will be the more challenging for some of you, the situation of what occurs when you have an electrolyte that partially dissociates but not completely. How do you count the number of particles in that situation? So those are our main examples here. Let's get started with the first easy example. And so this would have to do with the number of particles that occur when we start with 18,000 grams, or 18 kilograms, if you will, of glucose. And the molecular weight for glucose is given there at 180. And you can see the chemical structure on the right-hand side for glucose. And the only reason that's important is I want you to understand when we're talking about glucose, we're talking about something that is essentially not an electrolyte. It doesn't break down into component pieces. It stays like it is. Okay, so one molecule of glucose stays as one molecule glucose. It does not dissociate. It's a non-electrolyte. Okay, so getting back to this specific example, well, how many particles do I have if I start with 18,000 grams of glucose? Well, let's convert grams of glucose into moles of glucose. And we do that by dividing by the formula weight, because we know the relationship is that for every 1 mole of glucose, it is equivalent to the molecular weight in grams. All right, so remember, it's moles to grams or millimoles to milligrams. But in this case, we're in grams and moles. All right, so if we multiply 18,000 grams times 1 mole over 180 grams, the units of grams of glucose cancel, and we see that equals 100 moles of glucose. All right, so we are now in molecules of glucose. Now, we said, though, in solution, some particles, some electrolytes, will separate and dissociate into component particles. However, glucose is non-electrolyte. So if we start with 100 moles of glucose, then we'll multiply it by the fact that there are 0 particles that dissociate out of the 100 particles we start with. Because it's non-electrolyte, glucose does not dissociate, we get no dissociated glucose molecules. All right? So now, let's separate and count out how many undissociated particles there are and how many dissociated particles there are. Well, we said that we started with 100 moles of glucose total. Okay. From that, let's subtract the number of glucose molecules that dissociated, which we said was 0. Therefore, we have 100 moles of glucose that are not dissociated. All right. Let's count the particles of glucose that did dissociate, which I know you think this is so stupid, but we're going to have to do the same process through all of these different examples, so bear with me. We said there are 0 moles of glucose dissociated. Okay, so the total number of particles are going to be the number of particles undissociated plus the particles dissociated. Since we said we had 100 moles of glucose undissociated, we add to the 0 moles of glucose that dissociated, we have 100 total moles. All right. Since glucose does not dissociate, we have the same number of particles as we have the number of moles. Okay, so in this case, 100 moles. Right? Now, this was a very simple example of a non-electrolyte that doesn't dissociate. So clearly you get the same number of particles as you started with moles. Now, let's do something that's not quite so simple. Okay, we're going to start with now an electrolyte, sodium chloride. We are going to assume, though, 100% or complete dissociation. So as you can kind of see on the figure on the right-hand side, sodium chloride, a simple molecule of both sodium and chloride, when it's put into water, will dissociate, and you will get 2 particles for every 1 molecule of sodium chloride. You'll get 1 particle of sodium and 1 particle of chloride from 1 particle of the molecule sodium chloride. All right? So what does this mean? Let's use our example here. We're going to start with 5,850 grams of sodium chloride. So let's convert that to the number of molecules. We take the grams, 5,850, times the fact that we know that in 1 mole of sodium chloride, there is 58.5 grams, which is the molecular weight of sodium chloride. So when we multiply that across and divide by the 58.5, we get exactly 100 moles of sodium chloride. That's convenient. Now, how many of those molecules dissociate? Well, out of the 100 molecules that dissociate, all 100 will, out of the 100 molecules we start with, all 100 will dissociate because we said it completely dissociates. So the dissociation percentage is 100%. 100 particles dissociate out of the 100 particles total. So all 100 molecules of sodium chloride now dissociate, which means there are 0 molecules that don't dissociate. Okay, and we prove that by saying that the undissociated particles, if we start with 100 molecules total, and subtract the number that dissociate, which we said was 100 moles, then there are 0 moles of sodium chloride that are not dissociated. So there are no undissociated molecules. Well, now how many particles are generated from the dissociated amount of sodium chloride? Well, keep in mind, to figure that out, we know that it dissociates into 2 molecules, 1 sodium, 1 chloride. So to calculate that, we start with our 100 moles of sodium chloride and multiply it by the ratio of sodium moles in sodium chloride, which we said is 1 mole of sodium for every 1 molecule of sodium chloride. So now when we multiply that across, see that 100 moles of sodium chloride produce 100 moles of sodium. But what you may not have considered is the fact below that is that 100 moles of sodium chloride also produce 100 moles of chloride, because there's 1 mole of chloride for every 1 molecule of sodium chloride. So you also get 100 molecules or 100 moles of chloride. So the total number of particles will be the number of undissociated particles, which we said was 0 since we have 100% dissociation, plus the number of sodium molecules that were produced, which we said was 100 moles of sodium, plus the number of chloride molecules produced, which we said was 100 moles of chloride. So the total number of particles equals 200 moles. All right? Hopefully that's starting to see the routine in which we determine all of this. Now let's go a step further and make it a little more complicated. We'll stay with our sodium chloride example, but let's see what happens, what changes when you don't have 100% dissociation. And I kind of like the picture on the right-hand side here, because you can see that we have green negative molecule ions and we have white positive ions. So we'll have the cations and anions, but the point is that part of it dissociates. So you can see some plus white molecules and some green negative molecules that are surrounded by water that have dissociated and have separated, but they still surround a core of the undissociated particles that you began with. So we have partial dissociation. So what we need to do is count the total number of particles when you don't have complete dissociation. So we do it the same exact way. So let's use our example of sodium chloride here. We'll start with the total weight that we have, which is 5,850, times the fact that in 1 mole of sodium chloride, you have the molecular weight of 58.5 grams of sodium chloride. So once again, we are still starting with 100 moles of sodium chloride. Now the trick is to know how many of that 100 actually dissociate. We said that it dissociates at 80%. That means 80 particles out of the 100 will dissociate. Okay, so if we start with 100 moles total, multiply by the fact that on top we have 80 particles that dissociate out of 100 total particles, we see that we would have 80 molecules of sodium chloride that dissociate. Okay, so let's figure out again and count out how many molecules then didn't dissociate. So if we started with 100 molecules, subtract the fact that we do have 80 molecules that will dissociate, that means we have 20 moles of sodium chloride that did not dissociate. Don't forget about that. They're still there, clumped in the middle, surrounded by, essentially, ions that did dissociate. But we have 20 moles of sodium chloride that did not. Now, let's move on to the dissociated particles. Like we said before, now we have 80 moles of sodium chloride that do dissociate. So 80 moles of sodium chloride times the fact that there's 1 molecule of sodium for every 1 sodium chloride means we get 80 molecules of sodium. Similarly for chloride, 80 moles of sodium chloride times 1 molecule of chloride per sodium chloride means that there are now also 80 moles of chloride. Now remember, we need to add everything up. So we need to start with the fact that we had 20 molecules of sodium chloride that didn't dissociate. Those particles are still floating around. They didn't dissociate, but they're still there. So the 20 moles of undissociated sodium chloride plus the 80 moles of sodium that did dissociate plus the 80 moles of chloride that did dissociate, 20 plus 80 plus 80 equals 180 total molecules. So in this situation, we have 180 total molecules. All right. Now, let's make it just one more, the same process, but one more step of complication. And instead of doing sodium chloride, we'll do the same exact calculation about the number of particles in solution when you have 80% dissociation, but we will do that with zinc chloride. And the bigger difference for this is not only is the molecular weight different, but the molecular composition is different, because in zinc chloride, while we have 1 zinc, now we actually have 2 chloride molecules. So let's see how that changes all of this. We'll start it. It's the same exact process, though. We are starting with 13,630 grams of zinc. Let's multiply that by the fact that we know that there's 1 molecule of zinc chloride per its molecular weight, which is 136.3 grams of zinc chloride. Grams cancel, and we can see once again we are still starting with 100 moles of zinc chloride. The same as before, with 80% dissociation, that means 80 particles dissociate out of the 100 particles that you start with are 100%. So 100 molecules of zinc chloride times 80 particles that dissociate out of the 100 means that we will again have 80 moles of zinc chloride that dissociate. Okay, this is the same so far. Similarly, they will calculate the undissociated particles. That's the same as before. We start with 100 molecules of zinc chloride total. Subtract the 80 molecules that dissociate. We have 20 molecules of zinc chloride that did not dissociate. Okay. Where it gets different here is under dissociated particles. We do it the same way. Let's start with the zinc. If we start with 80 molecules of zinc chloride times the fact that there's 1 molecule of zinc for every 1 molecule of zinc chloride, we see that that would produce 80 molecules of zinc. Okay. Now, though, we start with 80 molecules of zinc chloride. We multiply by the fact that there are 2 molecules of chloride for every 1 molecule of zinc chloride because it's Cl2. So now we actually get 160 molecules of chloride ions. Now we'll do the same way to calculate the total number of particles in solution. Would be our 20 molecules of zinc chloride that did not dissociate, plus the 80 molecules of zinc that did dissociate, plus the 160 molecules of chloride that dissociated. So 20 plus 80 plus 160 gives us a total of 260 molecules. So hopefully you can see the process in which we calculated the total number of molecules from a given weight of any particular compound. The only thing we have to know is how much of that compound, the molecular weight of that compound, and the percent dissociation, because it makes a difference on whether it's 100% dissociated or less than 100%, and we would need to know what that percent is. So this is important information. You're going to see that we're going to apply this ability to calculate the number of particles in solution in our subsequent calculations. All right, now that we've had practice in counting the number of particles present with any sort of substance, now we can talk about the flow of solvent, and most often we'll just talk about water since that's the solvent typically we'll use. The flow of solvent across a semi-permeable membrane, because what we talked about before is osmosis says that water will flow in the direction of the highest concentration of solutes. So to illustrate this, in these images, we've got this picture of 2 kind of containers of fluid, in this case water. And we have a semi-permeable membrane on separating these two containers. Now, we start off on the left-hand side. You can see there's no flow of water, and there is just water on both sides. It's the same water on both sides. And you can see that the levels of the water are about the same. Okay, so there is no set movement. So what would happen if we put and replace the water on the left-hand side with a solution that contains 0.5 molar of glucose? Okay, 0.5 molar of glucose on the left and just pure water on the right. So clearly the only side between the left and the right that has any solute or any particles in it is the ones on the left. So clearly there's many more particles on the left than the right with the water, since water has no particles. So you can see here water would shift from the right to the left. And you can see the left-hand side with the glucose now has a much higher fluid level because water has been pulled over to help minimize or to equalize the osmotic forces produced by the dissolved solute glucose. Okay, this is kind of a classical example. So hopefully this makes sense that when you have, and again, the semi-permeable membrane keeps the glucose from being able to transfer over to the right-hand container. So the only thing that can happen to minimize the concentration, osmotic forces, is for the fluid to move. So, and that's why the water moves from the right to the left. Okay, so hopefully that'll set up these examples. So to begin with, now in this example, we've closed off that semi-permeable membrane. So we've got it's closed. So what we're going to do in a minute is we're going to lift up on that closure and allow it to be just a semi-permeable membrane. So what will happen to the fluid? What we want to know is on the left-hand side, we have a concentration of solution that contains 0.5 molar of glucose, compared to the right-hand side where we have the same concentration, 0.5 molar, but of sucrose. And what's important to understand is the molecular weight of glucose at 180 is much less than the molecular weight of sucrose on the right, which is 342. So, once we open up this dam, will the fluid flow from the glucose side to the sucrose? Will fluid move from the sucrose to the glucose, or will there be no net movement of fluid between those two? Keep in mind the glucose and the sucrose can't cross over. It would just be the fluid between those two situations. So, what would be the answer? The answer is there would be no flow at all. And the reason for that is that we have the same number of particles on the left as we have on the right. So keep in mind, what does molar mean? What is 0.5 molar? It means 0.5 moles per liter. And we have 0.5 moles per liter on the glucose. And we also have 0.5 moles of sucrose on the right. Since those are non-electrolytes, they don't dissociate, so they have the same number of particles. The fact that the molecular weight is different between glucose and sucrose doesn't matter when we're starting with the same number of molecules. Yes, those molecules don't weigh the same, but that doesn't matter. We have the same number of particles on the left as we have on the right. Therefore, the osmotic forces are the same on the left as the right. So we call this solution to be isoosmolar. The left hand and the right hand sides produce the exact same degree of osmotic force. Therefore, there is no net fluid movement from left to right. So you can see the fluid levels stay the same. All right? Hopefully that makes sense. Now, let's see what happens when we change this question slightly. It is the same setup with the same glucose and the same sucrose, but now what's different is I'm telling you the concentrations are different. On the left are 2 grams per liter of glucose compared to the right where we have 2 grams per liter of sucrose. Now we want to know the same question. When we open up the dam, which way will the fluid move, or will there be no movement at all? And you think, well, in the previous slide, they had the same concentration, and there was no movement. But the difference here is while we have the same concentrations, those concentrations are not in moles per liter, they're in grams per liter. And grams are not a measure of molecules, grams is the measure of weight. So to figure out how to answer this question, we need to convert the weight of our compounds, glucose or sucrose, to the number of molecules of those items. So let's start on top there with the glucose. If we have 2 grams per liter of glucose, to convert grams to moles, we divide by the molecular weight. So we're going to multiply by 1 mole on top, divided by 180 grams, and we're in moles. And just so that we have nicer numbers to talk about, let's convert moles to millimoles, and we'll just multiply our answer by 1,000. Okay, so 2 grams per liter divided by 180 grams gives us moles per liter, and then times 1,000 gives us millimoles. So on top, if we do that math, we see that our 2 grams per liter of glucose is the same as 11.1 millimolar. Our concentration in millimoles per liter is 11.1. Let's convert sucrose. Sucrose, 2 grams per liter times 1 mole on top per its formula weight, which is now 342 grams, times the 1,000 millimoles per mole. And we see that our actual starting concentration of sucrose is 2 grams per liter, but that's equivalent to only 5.8 millimolar. All right. So now, if we think about that, we have a much higher concentration in terms of the number of molecules of glucose. We have an 11.1 millimolar concentration of glucose compared to the 5.8 millimolar concentration of sucrose. So we would get net fluid movement from the right-hand side to the left. So we'd go from sucrose to glucose. You can see the volume of fluid in the glucose side has gone up because the fluid is trying to equalize the greater concentration of the 11.1 millimolar from the glucose back down towards the 5.8 of the sucrose. So that's why fluid now moves from right to left. So as a reminder, what drives osmotic forces isn't weight, but number of molecules. All of these questions will come back down to making sure you know the number of molecules in solution. All right. One more example here is, and this is an important permutation, same setup, but on the left-hand side now we have 0.2 molar of sodium chloride, and on the right-hand side we have 0.2 molar of sucrose. So what will happen with the fluid movement? Will it go left, right, or stay the same? And you think to yourself, well, He caught me last time about the weight, but now on this question, it's got the same concentrations, and they're in moles per liter. So I have 0.2 moles of sodium chloride on the left, and I have 0.2 moles of sucrose on the right. So clearly there shouldn't be any fluid movement, right? Well, that's not right, because that's not taking into account the number of particles that dissociate from the molecules. We said sucrose is a non-electrolyte. It's not going to dissociate, but sodium chloride is an electrolyte. So if we take that on top, we have 0.2 molar of sodium chloride, but that will dissociate into 0.2 molar of sodium and 0.2 molar of chloride. Since you get one sodium and one chloride from one molecule of sodium chloride, then the total number of particles is 0.2 plus 0.2, or 0.4 molar from the sodium chloride. 0.2 from the sodiums, 0.2 from the chlorides, total particles 0.4. Compare that to the sucrose that we said is not an electrolyte. So yes, you start with 0.2 molar, and that's exactly the total number of particles you have is 0.2 molar, because it does not dissociate. So once again now, if you base this off the total number of particles, we have 0.4 molar of particles on the left-hand side in the sodium chloride, compared to just the 0.2 molar of particles on the right-hand side with the glucose. So once again, your fluid is going to go from right to left to try to reduce the osmotic pressure from the higher number of particles present on the sodium chloride side. So again, the trick with this is, while we started with the same molars, they were not both there were differences in terms of one dissociates and one does not dissociate. And so the one that dissociates will generate more particles than the side that does not dissociate when you start with the same number of original molecules. All right. And so the last slide on this kind of brings this together in terms of why is this important? Yes, I think I understand now this whole thing about osmosis. What does it have to do with medicine? Well, that's where you need to learn the term tonicity. Tonicity means a solution that has the same osmotic pressure as specific body fluids. And particularly, we're talking about blood, so the plasma in the blood, or the ophthalmic, the lacrimal fluid in the eye tissue when we put ophthalmic solutions in. We're going to want to usually make our solutions, or the ones that we're getting to, that we're going to formulate. We want our drug-containing solutions that produce about the same osmotic force as is present in our biologic tissues. If we don't, and again, so an isotonic solution is a solution that has the same osmotic forces as that as our body fluid. What happens if we have too many particles? If we have a lot more particles in our solution as compared to biologic tissues, then that's considered hypertonic. Hypertonic solutions have higher osmotic pressures than body fluids. Or if we were to make our solution have many less dissolved particles than what you would expect to find in biologic tissues, then that's called hypotonic. And those solutions have lower osmotic pressure. Okay, and the reason that this is important is the classic example shown here for red blood cells. A red blood cell is a perfect example of a cell that has a semi-permeable membrane. If we put a red blood cell in a hypertonic solution, then the greater number of particles in the exterior of the blood cells out in the solution will suck fluid out of the red blood cell. The fluid will leave the red blood cell through the semi-permeable membrane in an attempt to lower the external pressure, the hypertonic solution, to try to bring it down. Okay, if we put conversely, if we put red blood cells in a hypotonic solution, then the fewer particles on the outside of the red blood cells have less force to be able to hold the fluid in. The fluid will be drawn inside the cells and potentially cause them to rupture as it tries to lower the concentration of all the dissolved solutes inside the cell. Okay, that would be bad. Hypotonic would be bad. Hypertonic would be bad. What we're trying to generally formulate our solutions to be is isotonic, so that when we put our solution around biologic cells and tissues, there is no net effort of forcing fluid one way or the other. That way the drugs can do what they are going to do without us affecting the cells in terms of the fluid solutions that we're bathing them in. So that's the idea. Then there are exceptions to when we formulate certain IVs and so forth. But in general, going forward for this chapter, certainly, we are going to try to make our solutions to be isotonic, meaning having the same concentration as typical biologic fluids such as blood and lacrimal fluid. All right, so now we understand that what we typically want to formulate our solutions, our drug solutions that we prepare, is to be the same as biologic fluids, and that refers to tonicity. How close they are to the actual biologic fluids would be isotonic. So now we need ways to evaluate our solutions that we're going to make with the amount of drugs that we're going to put in them to know how close to isotonic are they. We want to evaluate their tonicity. All right. There are two ways to do that. So just because one way would make it too simple. So for whatever reason, we have two ways that we can use to calculate and determine if our solutions are going to be isotonic or not. And then conversely, how to change them so that they are isotonic. We'll get to that in part 2 of this chapter 11. Right now, we just need to be able to evaluate and say, okay, how close to isotonic are we? All right. Two methods are, the first is the freezing point depression method, and the second is the sodium chloride equivalent method. They are both important. You are both held to being able to do these calculations using both methods. So you can't just ignore one and focus on the other. So let's do a quick overview first of both of those, and we'll go on each one at a time. Method 1 is the freezing point depression method. And this is done by comparing this one specific aspect of the colligative property of solutions is simply this, is that water freezes at 0 degrees Celsius. Okay? But biologic fluids are not composed just of water. They have all of these dissolved solutes in them. And what you need to know is that the more number of solutes that are dissolved in this fluid, then the lower temperature it takes to freeze them. Okay? So more stuff that's floating around in the water, the colder it has to get. So that's why we call this a depression. The depression was the fact that the water doesn't freeze at 0 anymore. It actually has to be colder than 0, less than 0 to be able to freeze. And the more stuff in it, the colder it has to get. All right? Now, remember, the whole point of tonicity is to evaluate our solutions compared to biologic fluids. And so isotonic solutions, the same concentration of solutions that freeze like blood, plasma, and lacrimal fluid, these freeze at a freezing point depression of negative, remember depression means negative, so negative 0.52 degrees Celsius. So here's the deal. That's what lacrimal or our biologic fluids freeze at. So if I just take water and add enough of my drug and maybe other stuff so that it freezes also at negative 0.52, even though the stuff I've added to my solution is very different than the stuff in blood, both solutions now freeze at the same exact point, negative 0.52. And since they do, then they have the same isotonic osmotic forces. So a solution that freezes at the same degrees as another solution has the same osmotic forces and then would be considered, in this case, isotonic, since we're talking about biologic solutions. Key concept. One thing we can use to formulate an isotonic solution is to make sure it freezes at negative 0.52 degrees Celsius, just like biologic tissue or fluids. All right? Now, let's move on to sodium chloride equivalent. This doesn't have anything to do with freezing point depression or anything else, but it does compare it back to something that we know. And what we know is that if we use sodium chloride as a solute into our solution, we know the concentration of sodium chloride by itself that makes water have the same osmotic forces as blood and lacrimal fluid, and that is 0.9%. 0.9% sodium chloride solutions don't freeze, but have the same osmotic forces as biologic fluids. So certainly that's one of the main solutions we use to make our drug compounds isotonic is to use sodium chloride, because we know 0.9% sodium chloride is isotonic. However, if we have drug in there as well, then it's not just pure sodium chloride. But what we can do is figure out how much our drug resembles sodium chloride. We can calculate the equivalent amount of sodium chloride that our drug produces. Okay, so we convert all of the ingredients we are putting in our solutions to the equivalent amount of sodium chloride that they resemble. Then we can calculate how much additional sodium chloride we would need to make it to be 0.9%. And I know that may be kind of blowing your mind at this point. Just understand that what we're going to do is determine the equivalent weight of sodium chloride produced by our drug. And what that is called is the E value. The sodium chloride E value is the weight of sodium chloride that is equivalent to 1 gram of our substance. So again, it standardizes it as the amount of sodium chloride per gram of substance. It doesn't mean our substance has that much sodium chloride. It's that our substance, our 1 gram of substance, mimics the osmotic forces produced by that amount of sodium chloride. So that's how we can use this E value to take our drug substance and convert it into an equivalent weight of sodium chloride, and then use that weight to be able to calculate up to what we know to be an isotonic amount of sodium chloride, which is 0.9%. So hopefully that wasn't a brief overview, but hopefully that makes sense, and we'll spend some time now using both of these systems. So, getting into the freezing point depression method for doing these sorts of calculations, a quick amount of review. Since we are going to be talking about colligative properties of solutions, let's make sure that we're still comfortable with our concentrations, because there are two. There is Molal and Molar. So just as a quick review, a 1 molal solution contains 1 mole dissolved in 1,000 grams of solvent. Remember, it's not in volume, it's per grams of solvent. Okay? Now we're going to cheat. We're going to make some assumptions here. And the idea is that a lot of our biologic solutions are actually a very dilute solution compared to non-biologic formulations. So in biology, since we're making usually very dilute solutions, then the volume, when we dissolve all of our electrolytes and all of our stuff, even that's in blood, the amount of it is actually so small that when we dissolve it in the water, it still only weighs about 1,000 grams. So what we're going to do to cheat here is say that since we're using water, and we know that the density of water is 1 gram per milliliter, and since our dissolved substances really don't occupy much volume, we can say that 1,000 grams of our solvent really occupies 1,000 milliliters, because it's water, and water has 1 gram per 1 milliliter, so 1,000 grams of water is 1,000 milliliters of water, and our drugs don't change that significantly. So we're going to say that 1 molal is equal to 1 molar for these biologic solutions. Therefore, and again, a 1 molar solution is one that's going to contain 1 mole per dissolved in 1 liter. So molar is 1 mole per 1 liter. All right. Therefore, since we know that 1 mole is equivalent to the molecular weight in grams of a solution, a 1 molar solution also contains the molecular weight in grams per 1 liter of solution. Okay? You know all of this. Hopefully, we've talked about some of this before, so let's go forward. But you got to keep those in mind when we talk about our concentrations. All right? Now, what is maybe a little bit different for some of you and is very important is this dissociation factor, which is abbreviated I in the upcoming formulas that we're going to be looking at. Okay? Dissociation factor. We said that electrolytes dissociate and produce more particles than non-electrolytes. So what we're going to say is that the dissociation factor I for non-electrolytes which do not dissociate is equal to 1. Okay? So the I for non-electrolytes is 1. The number is going to be larger for electrolytes because electrolytes produce more particles. For example, in the example of sodium chloride, since 1 molecule of sodium chloride produces 2 particles, 1 sodium, 1 chloride, the I value for sodium chloride is going to be 2. Another example, and this assumes 100% dissociation. Okay. The other example from before would be zinc chloride. There, since zinc chloride dissociates to 1 zinc and 2 chlorides, 1 plus 2 is 3, the I value for zinc chloride would be 3, since it dissociates 1 molecule into 3 particles. Again, this assumes 100% dissociation. Things will get more complicated if we don't have 100% dissociation. But for now, we know what the I value itself comes from. It's the number of particles that originate from the number of molecules. All right, and that depends on the type of molecule. Now we can say that 1 mole of a chemical has a freezing point, and we're going to say depression because it's negative. It's a reduction in freezing point. But 1 mole of chemical has a freezing point depression of minus 1.86 degrees Celsius times its I, or its dissociation factor. All right? So again, it hopefully makes sense. I is larger when you have more particles. Therefore, the reduction will be larger. You'll be multiplying your 1.86 by a larger number when you have more particles. More particles, more reduction in freezing point depression. Okay? So let's see this in action here a little bit. I will tell you, now that we know this, now we know that there is a reduction of 1.86 degrees for every I dissociation value, and the I depends on the degree of number of particles. What we're trying to get to, remember our overall target to be isotonic, would be a freezing point depression of negative 0.52. So that's how we can use this individual freezing point depression to determine where we need to get to, because where we need to get to is an isotonic solution, which freezes at negative 0.52. All right. So now we can set this up by using a proportion. All right, so this is an important formula to be able to answer some of these questions, where we're going to take the formula weight of the specific molecule, so the formula weight of that molecule in grams per liter, okay, is going to be set over this formula we just talked about, which is negative 0.86 degrees Celsius times its I. We set that equal to some target weight per liter, whatever we have for that, over our target freezing point. Okay, whatever depression we want. All right? So there's the formula. Let's use an example and fill this in. So the question reads, boric acid that has a molecular weight of 61.8 has a negligible dissociation. Think of it as a non-electrolyte. All right. What is the isotonic concentration in grams per liter of boric acid? So to set this up, let's use that same formula above, and we'll say, okay, of the product that I'm using, the boric acid, what is its give me a concentration of its formula weight per liter. We said its formula weight was 61.8, so we're going to put 61.8 grams per liter in the numerator. We're going to divide that by the fact that we have this expression of negative 1.86 degrees Celsius times, and in this case, it's times its I, its dissociation factor. We said in a simple example for a non-electrolyte that the I is equal to 1, so we multiply it by 1. All right? Now, that's a proportion we're going to set equal to some unknown or target weight. That's what the question is asking. What is the concentration of boric acid in grams per liter? So we set X on top, and X has the units of grams per liter, and we set that over the target freezing point depression. Well, what freezing point depression do we want to get with our boric acid? Well, we want boric acid to make our solution isotonic, and we know that an isotonic solution freezes at negative 0.52 degrees Celsius, so that's our target. So on the denominator, let's put a negative 0.52 degrees Celsius. So now, if we solve for X, would simply to take 61.8 times the negative 0.52, and then divided by the negative 1.86, we see we would get a numeric value of 17.3, and the units for that is in grams per liter. So this is really a powerful equation. We now know, based off of the kind of molecule boric acid is, and that it's a non-electrolyte, so its dissociation factor is its I is equal to 1, and we know its molecular weight is 61.8, we can then calculate to figure out if we just use boric acid, we would need 17.3 grams per liter to produce a solution that has the same osmotic forces as biologic tissues or blood or lacrimal fluid. All right. Let's move on a little bit and kind of make another permutation here. We'll still stick with non-electrolytes, but let's make it a little more difficult. So the problem reads, a solution of anhydrous dextrose with a molecular weight of 180 contains 25 grams in 500 milliliters of water. What is the freezing point depression of this solution? So now we know a concentration. We want to know at what point it will freeze. If it freezes at 0.52 degrees negative, that would be isotonic. So let's see what it freezes at and see if this is an isotonic solution or not. All right, back off. what's the first step? Let's calculate the concentration of the dextrose, because they gave it to us as 25 grams per 500 milliliters, but we need to express that concentration in grams per liter. So you can do this several different ways. What I did was set that equal to a proportion of X grams of dextrose, then over 1,000 milliliters. If I do that, 25 times 1,000 divided by 500, my final answer would be 50 grams. So in this sense, we're saying that our 25 grams per 500 mils is the same as if we had 50 grams per liter. But now our concentration is in grams per liter. So now we can use that same formula that we did before. And what we do on the left-hand side is the numerator is equal to whatever product we're using, in this case, anhydrous dextrose. Its molecular weight in grams per liter. So that's where the 180, the molecular weight, grams per liter goes on top. We're going to divide that by the denominator of our formula that says negative 1.86 degrees Celsius times its dissociation factor. And remember, this is still a non-electrolyte, so the I value here is 1. All right. Set that equal to the concentration we are using, expressed in grams per liter, which we just calculated was 50 grams per liter over X. And now we can see that if we solve for X, so if we take 50 times a negative 1.86 and divide that by 180, we can see that X equals negative 0.52 degrees Celsius. Lo and behold, remember, that is our target weight for an isotonic solution. So it turns out that an anhydrous dextrose concentration of 50 grams per liter produces an isotonic solution. Okay, that's the amount of dextrose we would need to be isotonic with biologic fluids. All right, so that was with an easier example with dextrose that was a non-electrolyte. So we're going to do the same thing with the sodium chloride and the zinc chloride example, but let's first calculate the dissociation factor when there is not 100% dissociation. And it shouldn't be mind-rending. We've covered through a lot of this already, but let's see how we get our actual I value. So let's start with the sodium chloride, again, with an 80% dissociation. Keep in mind, as we show on this slide here, the dissociation factor I is calculated by the number of particles divided by 100 molecules. It's not the same thing. Number of particles divided by 100 molecules. So if you remember back to our sodium chloride with 80% dissociation example, the number of particles came from 20 particles from the undissociated sodium chloride, 80 particles of sodium plus 80 particles of chloride. So 20 plus 80 plus 80 gave us 180 total molecules. So if we take 180 total molecules divided by the 100 molecules, we get 180 divided by 100. That would give us an I value of 1.8. So that's where that comes from. Okay. Now, what about the zinc chloride? It was similar, but a little bit different. Same formula, it's the number of particles divided by 100 molecules. So remember, for the zinc chloride, it was still the 20 molecules from the undissociated, but now we had 80 zinc molecules and 80 chloride molecules plus another 80 chloride molecules because it's Cl2. So 20 plus 80 plus 80 plus 80, all of that ended up being 260 molecules. So we take our 260 total molecules divided by 100 molecules. The I value now for the zinc chloride with 80% dissociation, we would use an I equals 2.6. So this was just a review of how to actually calculate the I for when you have when it's not just a non-electrolyte. So non-electrolytes equal 1. If it's an electrolyte, then this is how we calculate I, and we do have to factor in the percent dissociation to be able to calculate that correctly. So let's now apply that to some specific questions. All right. So let's do this question. It says, what is the freezing point of a 0.1% solution of zinc chloride that has a molecular weight of 136.3 that dissociates at 80%? So following up on our previous thing about the dissociation factor, let's apply that value now to calculating the freezing point depression of a 0.1% solution of zinc chloride. All right. Well, where do we start? Well, let's write the formula. It's the same formula we've done before now. We're going to say that the formula weight of the molecule we're using, in this case the zinc chloride, the formula weight of zinc chloride in grams per liter over the negative 1.86 degrees Celsius times the I value set that equal to our target weight in grams per liter over our target freezing point. All right, so let's fill in that formula. So first thing let's do, though, is we need to convert our concentration of zinc chloride solution from a percent into grams per liter. So remember, we were given in the question that our concentration was 0.1%. So what does that mean? That means we have 0.1 grams for every 100 milliliters. What we want, though, is in grams per liter. So let's just multiply the top and the bottom by 10. So what we would get on top is 1 gram, and on the bottom we would get 1,000 milliliters. We have 1 gram per 1,000 milliliters. Since 1,000 milliliters is a liter, we have a concentration of 1 gram per liter. So hopefully you're able to follow that okay. All we've done is convert our 0.1% and restate that as the same as 1 gram per liter. So now we can go ahead and fill in all of the numbers in our formula. Because what we know is that the molecular weight of zinc chloride is 163.3, so we have 163.3 grams per liter on top, over the negative 1.86 degrees Celsius times I, and what we just did on the previous slide was calculate that the I for zinc chloride with 80% dissociation was 2.6. Okay, and if you don't remember where that came from, just drag back to the previous slide and review that calculation for the zinc chloride. We just completed that one, and we said that the zinc chloride at 80% dissociation was 2.6. Okay, let's set that equal to essentially the concentration we have of the zinc chloride, which was 1 gram per liter. And now what we're solving for on the bottom, what we set as X, is the actual freezing point depression that will be caused by that concentration. All right? So if we solve for X, we take negative 1.86 times 2.6 times 1 divided by 136.3. X numerically would equal a negative 0.035 degrees Celsius. So this solution of 0.1% zinc chloride essentially causes a negative 0.035 degrees Celsius depression. One interpretation we could make at this point would be that that certainly is not an isotonic solution, because if it was, we would expect it to have a freezing point depression of negative 0.52. So clearly this is a good example of a hypotonic solution. It does not produce near the freezing point depression we would have predicted for an isotonic solution. All right, and that was the answer to this question. All right. Moving on now, clean your mind. Take a couple of deep breaths, because we are changing now to method number 2, which was to do the same sorts of calculation. That is, to be able to evaluate the tonicity of our solution. That is it hypotonic? Is it isotonic? Is it hypertonic? But instead of using the freezing point depression colligative property, we're going to use sodium chloride equivalents. So just as a little background, I've kind of said some of this before. Sodium chloride is used as our reference electrolyte because we know how much sodium chloride is isotonic. We know that a 0.9% weight per volume solution, that means 0.9 grams per 100 milliliters, or if we express it per liter, multiply the top and the bottom by 10, that's the same as 9 grams per liter. So either one of those concentrations would produce the same osmotic forces as an isotonic solution, as biologic fluids. Right? We also know that sodium chloride has a molecular weight of 58.5, and we can assume that its I value is 1.8. Okay? So the nice thing is we don't have to go back and recalculate that for sodium chloride every time. Its I value is 1.8. We can just use that in these formulas you see below. All right? So there are tables of E values for many chemicals. And again, an E value represents the weight of sodium chloride of that drug, the weight of sodium chloride that is equivalent to 1 gram of your particular drug. Okay, so it's a variable amount of sodium chloride, whatever the value is, per gram of your drug. Okay, and there in your textbook in table 11.1, they give E values for a variety of substances. However, you can calculate your own E value. Okay, and this is kind of an important thing to be able to do for the test. It's something you might need to do. And I'm going to skip the derivation. So the middle part of this slide gives you kind of the derivation of this, but let's just drop down to the bottom. What you need to know. To be able to calculate the E value of any chemical, what you would do is take the number 58.5 divided by 1.8, then multiply it by a fraction that consists of your I value for your substance on top, so the dissociation factor for your chemical on top, divided by its molecular weight. Okay? And so that's typically how you would do that. So, and the derivation is above. And just so you know, 58.5 comes from the molecular weight, obviously, of sodium chloride, and then it's 1.8 is its dissociation factor. And then you times it by the I of the substance divided by the molecular weight of the substance. And that's how, when you're all done, what you get is a value that represents that value is the grams of sodium chloride equivalent to the 1 gram of your drug. All right? So that's how you can do it. Let's just use that formula and see how it works. So the question is important. It says, boric acid that has a molecular weight of 61.8 has negligible dissociation. We'll treat it again like a non-electrolyte. Determine the E value for boric acid. All right, so how much sodium chloride is equivalent to 1 gram of boric acid? That's what we're asking. Not how much sodium chloride is in the boric acid, but when we dissolve the boric acid, that amount, 1 gram of boric acid, would produce the same osmotic force as how much sodium chloride. Well, let's solve that using our formula. Remember, it's a pretty simple formula. You take 58.5 divided by 1.8 times, now we said that the I value, or the dissociation factor for boric acid, since it's a non-electrolyte, is going to be 1. So it's 1 in the numerator divided by the molecular weight on the bottom, which we said was 61.8. So 58.5 divided by 1.8 times 1 divided again by 61.8. You do that math, and numerically you get a value of 0.52. And let's interpret that, because here's what's confusing, is that the E values in the tables will be unitless. It will just have a number like 0.52. It's really important here that you'll be able to interpret that as meaning 0.52 grams of sodium chloride per gram of boric acid. So make sure you can interpret those E value numbers. All right, so let's do the next example, which is for zinc chloride, which we said has a molecular weight of 136.3, and again, 80% dissociation. This is important in determining its dissociation factor, or I value. But what we're trying to solve for is determine its E value, which again means how much sodium chloride is equivalent to 1 gram of zinc chloride. This solves exactly the same way as we did before, so we'll set this up. We would do 58.5 on top, divided by 1.8 times, but now what goes in the numerator again is the I value for zinc chloride with 80% dissociation. As we've said before, the way we determine that is we have 20 particles that are not dissociated, plus 80, plus 80, plus 80. So you add all that up, you get the 260 divided by 100 particles or molecules gives us an I value of 2.6. So we've done this before again a couple of times. Just a reminder, the I value for our zinc chloride example is 2.6. So we put 2.6 and then divide it by the molecular weight of zinc chloride, which we said was 136.3. So 58.5 divided by 1.8 times 2.6 divided by 136.3 should give you the numeric value of 0.62. And can you interpret that? If we just said the E value for zinc chloride is 0.62, you would set that up as meaning 0.62 grams of sodium chloride per gram of zinc chloride. All right? All right, now let's kind of continue this application here and try it in a different way, because now what we want to do is calculate the percent concentration of boric acid solution that is isotonic with body fluids. Okay, this is kind of where we're leading up to. All of these skills get to the fact that, all right, if I have boric acid and I want to make an isotonic solution, what concentration of boric acid is that? Okay. What I need to know and what I was given here was that the E value for boric acid is 0.52. All right? All right. So let's remind ourselves, what is our target? How much sodium chloride do we need? Okay. Well, we said that isotonic sodium chloride is 0.9% weight per volume. That would be equivalent to 0.9 grams of sodium chloride per 100 milliliters. Thus, what we're saying is that for 100 milliliters, we need to know how much boric acid weight would be equivalent to 0.9 grams. If we have enough boric acid that it is equivalent to 0.9 grams, and we put that into 100 milliliters, that's going to be isotonic. All right. So now what we want is the amount of boric acid that's equivalent to 0.9 grams. All right. Well, we have an E value, so let's restate that E value using units, okay? So if they just say the E value is 0.52, I've been harping on this, we would rewrite that as 0.52 grams of sodium chloride per 1 gram of boric acid. That's the important conversion factor that we need to use. So let's set up our final equation, because what we said before is that for 100 milliliters, we would need 0.9 grams of sodium chloride. So let's start with 0.9 grams of sodium chloride and multiply by the fact that for every 1 gram of boric acid, it's equivalent to 0.52 grams of sodium chloride. That way, grams of sodium chloride cancel. So if we take 0.9 times 1 divided by 0.52, our answer numerically would be 1.73 grams of boric acid. And since that was the amount we needed to be the same as 0.9 grams, which is the amount that makes 100 milliliters isotonic, then the 1.73 grams is what we need per every 100 milliliters to make it isotonic. 1.73 over 100 is the same as 1.73% weight per volume. So what we have just calculated is that we would need 1.73% weight per volume concentration of boric acid to produce the same osmotic forces as 0.9% sodium chloride, which we know to also then be isotonic with biologic fluids. So that means that 1.73% boric acid would produce an isotonic solution. All right, our last question is to perform these same calculations again, but now using zinc chloride. So the question says, calculate the percentage concentration of a zinc chloride solution that is isotonic with body fluids, given that the E value for zinc chloride that we calculated previously equals 0.62. So I'll try to go through this quickly. It's the same idea. We want the amount of zinc chloride that is isotonic, which means it's the same amount as sodium chloride, 0.9% weight per volume, which means we need 0.9 grams per 100 mil. So our target for sodium chloride is 0.9 grams. All right. We know that the E value for zinc chloride is 0.62. So we would reinterpret that or express that as 0.62 grams of sodium chloride per 1 gram of zinc chloride. So now we can use is the fact that since our target is 0.9 grams of sodium chloride, let's multiply that by the fact that for 1 gram of zinc chloride, there would be equivalent to 0.62 grams of sodium chloride. Therefore, 0.9 times 1 divided by 0.62 equals numerically 1.45, and our units would be grams of zinc chloride. Thus, we've just shown that 1.45 grams of zinc chloride is equivalent to 0.9 grams of sodium chloride. Therefore, 1.45 grams of zinc chloride per 100 milliliters is the same as 1.45% weight per volume, and that's the concentration, 1.45% weight per volume of zinc chloride, that is going to be isotonic. So hopefully this is an important, that ends this lecture. It's an important review of some of the fundamentals that we're going to go forward to in the next lecture and start to apply as we now finally get to formulate prescriptions for compounding IV products or ophthalmic solution products that we want to make isotonic with biologic fluids.